We did energy yesterday and the day before, right? We did a problem in energy. Yes, we did the problem in we did the problem in energy, right? You guys all think? Not yesterday, the day before yesterday. The day before yesterday, we did this problem, didn't we? Where we had the ball.
Yeah, we did.
Yes, we did.
I don't know if we finished.
Okay, do you have it? Okay, so I'm going to let you guys finish it in the next 3 minutes. So finish that problem. Let's go. Let's finish that problem.
Is it this problem? The one with the hill is 100 meters up.
Yeah, so the hill is 100 meters up.
Okay.
Right? And I said what? And the point B was how far up?
34 meters.
34 meters. That sounds about right. And that's point A, point B, and point C. And what did I ask you for? I asked you for a bunch of stuff, didn't I? I asked you for energy total. I asked you for PE at A, B, and C. I asked you for KE at A, B, and C. And I asked you for the velocity at A, B, and C, didn't I? Yeah? All right. So do that. I'm going to give you guys 3 more minutes. You should be able to solve that in 3 minutes. Let's go. What's your equation? You're going to, every time, guys, don't split up. Don't split up the kinetic energy and the potential energy equation. Make it one big equation. Potential energy plus kinetic energy equals total energy. I see a lot of people going, well, here's my kinetic energy, and here's my and they separate it out. Don't do that. It's PE plus KE equals ET. Because that statement is true where?
Wait, did you give us the mass of the ball?
I did. The mass of the ball was what?
I don't know.
10 kilograms. Kaylee, that equation is good for where? Everywhere. So you're going to write that equation for 3 times. Right? Okay, guys, finish this up because we're going to move on to another. I'm going to throw a couple more things on here. Yeah.
I remember Sean told you yesterday that he was in John's or something.
Okay, that's fine.
It's calculus.
What?
On this case for gravity, do you use the negative in or just keep it 9.81?
Always negative.
Okay.
But your height, for potential energy, your height's actually going to be negative because, right? Your height's going to be negative, right? Because the potential to go down. I want to stop this stuff. Right? Miss Burkhead had she started to play Eye of the Tiger.
Yeah, I remember that.
Right? And so I really wanted her to play. Where's my volume? You guys, so Starbucks years ago had this great ad campaign. Starbucks. It was based on the Eye of the Tiger song.
Can we see it?
Yeah, I'll play it for you. All right, you guys keep working. You keep working.
You can find it.
Okay. So let's talk about, guys. It's now recording. Quiet, guys.
Is it recording now?
Okay. Shh. Hey, everybody. All right, let's work the problem. So, guys, are you gonna? Okay.
I'm listening.
I'm going through this, and you're responsible for it. It's going to be on the problem set and on the final. Okay. Did everyone get answers?
Yes.
Was everyone able to complete it?
Yes.
Okay. Do you want me to go through it?
Yes.
Okay. I'm gonna breeze through it quickly. Look.
Okay.
P plus, but everyone's gonna be quiet. P plus K equals energy total.
I'm so sad.
Okay. For A, B, and C, Kaylee, when is this equation valid for? Everywhere. So the PE plus KE equals ET at A. Okay, Zach and Siva. Zip it. What's my PE equation? Someone help me out. You guys tell me what to write. You guys tell me what to write.
MGH.
Thank you.
No problem.
That's it. That's all I'm gonna write.
Equals PE.
Wait. No. This is what, guys, don't say MGH equals PE. Right? Use the equation. If you split it up, because the next thing I'm gonna do is gonna kill you.
Oh, you're just,
Yeah. Right. Okay. And I don't mean to jump on you. I've seen people do this, and I know it's gonna be a mistake. So I'm trying to get you not to do this. So I'm finishing out the equation, I'm breaking it up. PE is MGH. So what's the next thing I'm gonna write?
Plus
Thank you.
1/2 MV squared.
Equals
ET.
ET. What is the point that I know the most about?
A.
A. So let's do A. So what's my mass?
10 kilograms.
10 kilograms. What's my G?
Negative 9.81
Negative 9.81
meters
per second squared. What's my height going to be?
100. Well,
It's
negative.
going to go down to negative 100 meters. I know I'm doing this wrong. Okay, all right. Plus what? Go ahead. I'm sorry?
1/2.
1/2
in
times.
10 kilograms.
Uh-huh.
And then the velocity is going to be distance divided by time to the distance. Would it be 100?
Okay, at the very top, my velocity is going to be 0.
Yeah.
Right? It's going to be 0. And that's going to be squared. Equals my energy total, right? Okay.
because the potential energy is 0 at this point,
Right,
right?
because my not my potential, but my kinetic energy. My kinetic, yeah, I know what you meant. Your kinetic energy ends up being 0, guys, right? So, hold on. See this? Okay, and here's the deal. I want to be very clear about this because the way the book does it, the book says, oh, well, 9.81 is actually going to be positive and not negative. I don't, it's a fudge factor to get the value to be that. I'm sorry.
Then the 100 would be positive.
Yeah, and then the 100. So all I'm saying, because you got to get positive energy at the end, okay?
Yeah.
So that's where I'm at. So okay, so and that was just bugging me because I was
It's
like,
going to be 98.10.
all right, so it's not, it's going to be,
You got that too.
it's going to be, what is it? It's going to
9,810.
9,810 joules, right? Plus 0 equals my energy total. So my energy total is 9,810 joules, right? Everyone get that number?
Yeah.
Okay. That energy total, is that different at B or C?
Same.
No, it's the same. Okay.
Oh man.
Okay. See the magic of physics? I told you, it's all going to... Magic, the solution. When you are stranded on that desert island, all you need to know to solve that physics problem that's going to save your life.
So, yeah.
So PE, so I'm going to do it now at B. At B. What's my equation for B? PE what?
K,
Plus KE equals
ET at B.
ET. This is going to be for B. So let's break down the equation. What is it?
MGH.
Plus 1/2 mv squared equals ET.
Okay, real simple. Now, let's plug for B. What's my mass at B? Does it change? 10 kilograms. Okay. My acceleration, 9.81 meters per second squared. What's my height at B?
I put 66.
Okay.
I mean 34.
Well, it's the height relative to what?
Ground.
The ground. Yes, right. And comes back to the electrical, right. Yep, negative 34 meters. Plus,
That's the potential energy being smaller.
what's plus 1/2, what's my mass? 10 kilograms. What's my velocity at, we don't know. That's what we're looking
Well,
for.
we know what ET is, so.
He is a little green guy from outer space. Yeah.
Green.
Wah,
He's
wah,
not green.
wah, wah.
He's great. He's like.
Okay, he's pea soup greenish gray.
He's not green.
Okay, so my ET, what's my ET?
9810.
1898 10 joules. Phone home.
He looks like he's
Exactly.
dressed like Mother Teresa. That's why.
Okay, so what's my value here? It's 10 times 34. 10 times 34 times 9.81 is 3335.4. So it's 3335.4 joules. Plus, I have 1/2 times 10, which is 5v squared equals 9810 joules. That means that 9810 minus 3335.4 divided by 5 square root velocity is what? 35.98. Velocity is 35.98 meters per second. By the way, we did this problem before, didn't we? And how did we solve these problems before? Using what method? Think of the ball. Rather than being a ramp, if I drop the ball, what did we use? We used the kinematic equations, right? We use velocity, delta x final equals x initial plus v naught times v initial times t plus 1/2 at squared, right? Yes, yes. V final squared equals v initial squared plus all those equations. You can solve the exact same thing that way or with energy.
I'd
It's
rather
your-
do it this way.
It's actually pretty decent. It's an energy piece, right? So either way.
Pretty easy, yeah.
Okay, but this is again, it's all 5 different ways to do the same thing. I might ask you on the final, show me 2 different ways to solve this problem. Wah, wah, wah.
Maybe not.
That's not a good idea.
That's not a good. Okay, note to self. Okay, so what? Thanks. What's my PE at A? What's my PE at A? What's my potential energy at A, guys?
9810.
What's the potential energy at B? 35.4, right? What's the KE at A?
0.
What's the KE at B?
6474.46.
What?
6474.
Oh yeah, the two, yeah, right. So you know that, right? So the KE at B is equal to my 9810 joules, which is my total, minus ET.
Wait, what is that?
My kinetic energy is equal to my total energy minus my potential energy, right? Yeah? So that's equal to 9810 minus my PE of 3335.4, which gives me a total of what, guys? 6474.6 joules. You guys see that?
Wait, but yeah.
That's my KE at B.
Oh, okay, yeah.
Yes. That's all we're balancing out. That's what I'm asking you to do. Just fill in the table. Right?
Oh, I see you got. Oh, okay, you got.
Right?
Yeah.
Yes, I did. I asked you for A, B, and C.
Yeah.
Okay. So we have the velocity at A, we have the velocity at B, we have the KE at B, the PE at B, and the KE at A and the PE at A. We have all of those.
We don't have C.
We don't have C now. Let's do C.
All right.
All kinetic energy.
Okay. So again, don't take a shortcut. I'm going to count off.
I won't.
If not for the sake of your own logic, don't do it because I'm going to take points away. So what's my equation for energy at C?
It's the same thing.
P plus KE equals ET, right? What is and so I break it down. Let's go.
MGH plus 1/2 MV squared
Equals
ET.
ET. So MGH. What's my H at C?
0.
0. So that goes to 0. 0 plus 1/2 times my 10 kilograms times my velocity squared. Is that what I'm looking for? Yes. What's my energy total? Do I know it? 9810 joules. Now look, my PE at C is what? 0. Okay? So that means my KE is what? 9810. Woohoo! And then my velocity is equal to the square root of 9810 divided by 5. So 9810 divided by 5, square root, that means it's equal to 8.85.
You did extra step. You did like
9810 divided by 5.
square root.
Oh, what did I not? I'm sorry, yeah.
You like
Oh, divided by 10, I'm sorry. Divided by 5 is 44.29. So it's 44.29. 44.29 meters per second. Right? And this is all for C. By the way, see how I organize my work? It may not be, it's not the cleanest, but it's because my handwriting stinks.
Give us space on the test to organize our work.
I can't. I can give you extra paper. You can have extra paper to organize your work. I need to draw the picture large so you can see it. If I make it this small, you're like, I can't see this, Mr. A. But listen, I'll tell you, there are people on those tests who can organize it, don't write so big. I'm with you, Zach. I'll give you an extra piece of paper. No worries. But on that piece of paper, organize the work.
Like last test, my work was not organized whatsoever.
So that's not good.
Last test I didn't have to work.
Okay.
So is this gonna be, is the problem set gonna be like this, or is it not gonna be like
That's a very vague question. Is your question going to be vague, or is it, what does that mean? Is it going to be? I don't know. I'm
this?
sorry.
Is it gonna be like this kind of question, or is it gonna be something different?
I'm going to ask you about the meaning of life. No, meaning like.
I get exactly what you're saying.
I know. I'm just yanking your chain. No, I'm gonna ask you some questions. It's using the basic concept. I'm gonna push you a little bit. Yes, I'm gonna push you a little bit. Okay, there we go. All right. So, all right. I'm gonna go. Let's do the next thing. Ready? Here's another thing that's important to know. We have different things. We have potential energy of height. We also have potential energy due to a spring. Everyone knows what a spring is, right?
Like a trampoline.
And the spring on a trampoline, right?
Some trampolines don't have springs.
Yeah. Okay, here's a spring, okay? Here's the thing about springs. The force required to compress a spring is equal to K times X. Now, what is K and what is X? X, if I have my spring, let's say I've got my spring here. Okay. Oh, that's a really horrible spring. One more time.
Draw it with a spiral.
Sir, if we have class outside,
I think we should totally have class outside, yes. Okay. Okay, here's my spring. It's a really cruddy spring. I apologize. Okay. The amount that I compress. So here's my spring uncompressed. Here's my spring compressed. But it's smaller.
Oh,
It's shorter.
Because you put like
Yes. This is uncompressed. This is uncompressed.
you see.
Compressed. Okay? The distance, I compress it, that is X.
Oh,
There's a certain amount of force required to compress it a certain distance. Based on the type of the material of the spring, the outer diameter of the spring, this outer diameter, and the diameter of the wire itself, So there's a diameter of the outside, the OD. There's the diameter of the wire, and the material. Those three things affect the spring constant, which is K. So this is our spring constant. If I were to go and order a spring, I might go to McMaster Car. Some of you have been here to the site before. This I can order everything under the sun. Okay? Yes.
Anything.
Get,
A gun.
I think Sherry Duncan's gonna come after you now.
air guns,
No, I don't want an air gun.
battery-powered grease guns, blasting guns,
Okay.
cable tie
Here we
guns,
go.
foam guns. Okay?
Like a real gun?
Springs. Shh. Okay? All right. Springs. There are different types of springs. There are constant force springs. There are compression and die springs, extension springs, torsion springs, disc springs. Disc springs are cool. Okay, disc springs are, as you compress them, they spring back. It's for hardware. If you're screwing something down, you want to put some tension on that screw. You put the disc spring in. Okay? Compression spring. Here's a compression spring. You can figure out all the different. Notice you got overall length. You have your compressed length. You've got your outer diameter. You have the wire diameter, and then the force. Now, what that means, if I go into my compressed spring, they should give me a spring constant. Do they give me a spring? They don't. They don't give me the spring constant. What they give me is overall force. So I have an outer diameter. I have the wire diameter. I have my overall length, and I have my material. Those things will actually create. Oh, they don't show a picture. They'll generate how much force is there. So the force that's required for any spring to compress a certain distance, that's K. So if I know the distance of the spring and I know the force, K equals F of the spring over X. Right?
If that's a F of the spring, force of the spring over X.
Mm-hmm. Okay. Oh, okay. All right. Without going into the derivation, because I just don't want to waste time on that. Okay. There's an energy to the spring. The PE of the spring. So if this is the force, this is the force of a spring. Force of spring. That's the spring equation. It's Hooke's, and this is, I'm not going to require you, but this is Hooke's law. Okay, Hooke's law. Who? I don't remember his first name. I'm not a historian. I'm sorry. Okay, the potential energy of the spring is equal to 1/2 kx squared. Okay, and what it comes from is it comes from the work equation. It comes from the idea that work is equal to force times distance, but the force changes over time. So we have an average, because the force to go a small distance is not the same force as to go a bigger distance, right? So you have an average. So it's 1/2 k times x, and that's why we get the p. But here's the thing. So I've got p of the spring, the potential energy. So as I compress that spring, I store energy into it. I have the potential for that spring to do some work, don't I? Yeah. Right? Okay. So if I may start over here, we now, if I look at the total energy of something, I've got P, or the types. If I have the types of energy, I have kinetic energy, I have potential energy due to height, and potential energy due to spring. David Dentino. A problem. So let me do one problem with spring, and then we'll talk about what we're doing here.
We have 5 minutes.
Good. So I have a device here, okay? Now here's the deal. In this device, there's a spring. Okay? On a little platform. Okay?
Yes.
Robert.
I was thinking the size of shipping.
You what?
You didn't even know what he did? Crazy.
I said Robert Hook.
He did say that.
I don't know.
Okay, so here's my ball. Super Happy Fun ball. At this point, the spring is uncompressed, so there's no energy stored in the spring. Then I take that same spring, and I put the ball in the spring. I compress the ball. I put the ball in, and I compress the spring a certain amount, and I compress it from here to here, X. Okay? So there's two things that I can ask you. If I give you the spring constant, okay, and let's say the spring constant is what would be a good spring constant? Let's say it takes 10 newtons. Let's say it takes 10 newtons to compress it 0.2 meters. That means my spring constant is 10 divided by 0.2, which is 50 newtons per meter. Okay, that's my spring constant. If X, I'm going to compress that 0.15 meters, I'm going to ask you two things. What was the force required? What's the force required to compress it that amount? And how much energy is stored in the spring? So again, force equals K times X, force of a spring, and the energy of a spring, or the PE of a spring, is equal to 1/2 kx squared. Okay? Quickly do that. Give me like in 30 seconds or a minute, figure out the force of the spring and PE spring. Go, 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 go. Go, go, go. Because I'm going to give you a problem here, Mr. Dentino. That's going to show you what a problem that I might ask on the problem set.
So is the
There you go.
No, you're
Okay, so an example of a problem I might ask you is this. Given a ball compressed in with a certain mass, okay, compressing that spring a certain distance, I can ask you how much force is required to do it, and once it's released, how high does it go? Because what's going to happen when the spring is released? What's going to happen to the potential energy in the spring? Where's it going to go? Into the ball, giving the ball what kind of energy? Kinetic. So the spring is going to have a total, the potential energy of the spring is going to be your energy. It's going to transfer into the ball, giving it a Ke plus PE, where PE is 0 for total energy, and then you can figure out the height. And the velocity at different heights. You see what I'm going? That's the kind of equation. And that's very simple. This is what we're doing all year. Combining things together, right? Okay. See you guys, some of you guys tomorrow. See the rest of you guys on Monday.